Hello everyone, I'm Vivekanand Thagri, your chemistry instructor. In today's lecture, we are going to take a look at the copolymers, the process of copolymerization. What exactly is a copolymer? What are the difference in the properties with respect to the homopolymer, followed by the rubbers and the synthetic rubbers, right? So as we start with this session, we shall start with the copolymers. Now try to understand it in a very simple manner. Let us assume that we have a monomer. And let me say that this is a monomer A, right? Now, let's say that this monomer A is going to react or get polymerized with the different monomer. And let me call this as the monomer B, right? So here we have the monomer A, and over here we have the monomer B. So when a process of polymerization occurs between two different types of monomeric units, over here I have taken into consideration of two different types. We can say as more than even two different types of monomers when they get polymerized. And thus, when they get polymerized in order to yield a polymer. Now, the polymer that has been formed because it has different monomeric units, such as monomer A and the monomer B, right? Now, this particular polymer that gets formed because of the polymerization between different types of monomeric units, these particular polymers, we call them as the copolymer, right? So, now, when we take a look at these particular copolymers can be either prepared by step growth polymerization, or it can be prepared through a chain growth polymerization. Okay, now, whatever it is, whether it is a step growth or whether it is a chain growth polymerization, these polymers, okay, a particular chain of copolymer contains all the specific monomers which are involved. Okay, a simple chain contains all the monomeric units. Now, when we observe, let's observe an example. For this case, I would like to take into consideration of a Buna S. Okay, now Buna S. Buna S is formed through the two different polymers indeed. Those are CH2 double bond CH single bond CH double bond CH2. So this is 1,3 butadiene, right? Now, when n number of 1,3 butadienes are going to get polymerized with styrene molecule. Now, styrene molecule is nothing more like a aromatic benzene system connected to CH, the double bond CH2, right? Now, when this particular polymerization occurs, it gives a rise to CH2, okay, single bond CH, double bond CH, single bond CH2. Now, this is this particular carbon over here. Okay, now this carbon reacts at this particular point. As it reacts at that point, what is going to happen is, you'll observe CH, the CH is connected to the aromatic system, right? Now, the CH further is connected to CH2, the double bond gets converted into a single bond and it results into the polymer. Of course, this is a copolymer, and this particular copolymer that you see is a Buna S. Now over here, you need to understand the differences in the properties. Okay, the difference in the properties we shall discuss in the next slide. So we'll observe every single point that we have discussed over here. So under this particular process of the copolymerization, it is a polymerization reaction in which the mixture of more than one type of monomeric unit or species are allowed to polymerize, resulting polymer or the product, we call it as a copolymer. The copolymer can be made by the chain growth polymerization, which we have already discussed as well as the step growth polymerization. It contains multiple units of each monomer that has been used in the polymeric chain. Okay, for example, the mixture of 1,3 butadiene and the styrene can form a polymer, that is a copolymer, which is called as the buna-S, right? So the buna-S is nothing more than actually it is the butadiene styrene polymer. Now, let's try to understand the differences in the properties. Now here, try to get this particular point. When you have a copolymer, let's say this is a copolymer which is formed, okay, which is formed because of the two different monomeric units which are involved, right? Now, when we compare the properties of these copolymers, okay, the properties of these copolymers shall compare with the homopolymer. Now we already know that the homopolymers are the polymers which are formed from only one type of the monomeric units. When we observe its properties, copolymers are being formed to have better mechanical and physical properties when we compare to that of the homopolymers. Okay, so here what we'll observe is it has the better properties with respect to the physical or mechanical properties, right? While when we observe about the homopolymers, these are quite soft when we compare to that of the copolymer. For example, when we take a look into polystyrene. Now, polystyrene. So here, polystyrene is actually made up of all the styrene molecules. So this is a styrene, correct? So when styrene undergoes polymerization. So this particular styrene, CH, single bond CH2, and this particular chain actually continues. So this is our polystyrene, correct? Now this polystyrene, when you observe, it is usually soft. Okay, it has a very good electrical insulating properties. So it is a good electrical insulator. It can be heated, molded back into the different shapes. So therefore, it can be molded into different shapes, toys, combs, radio, and television parts. While when you observe about the Buna-N, okay, which we have already seen in the previous slide. So the Buna-N, okay, sorry, the Buna-S, what we have, this Buna-S is actually a very good substitute for the natural rubbers. Okay, so as a result of which what we see is this particular Buna-S has a very good abrasion resistance. It has a very good high load bearing capacity, and hence it is used in preparation of tires. It is used in preparation of floor tiles, footwear components, cables, insulations, etc. So here is all what we see about this. So the main differences you have observed, right? So when we go further, so now we shall discuss about the rubbers. So in the rubbers, of course, we have the two different types. One, what we call it as a natural rubber, and the another one is the synthetic rubber. Okay, so when you observe, first we shall speak with respect to the natural rubber. Okay, so natural rubbers. This natural rubber is a natural polymer, right? Which is actually obtained from latex. Now, latex is nothing more than a milky white precipitate or a solution which we obtain from a rubber plant. Okay, so a rubber plant, what they do is, if we consider this as a bark of a rubber tree, okay, now a insertion, a cutting is done from a left to right at a particular angle, due to which the liquid, the latex starts to flow out. Okay, so when it flows out, they collect it in a particular container. Now, this particular latex, what they get, they dilute this. Okay, they dilute this adding water. And after adding water, what they do is they are going to add certain amount of the acetic acid. When they add acetic acid to it, they churn it very well and they leave it to dry, which usually results in the clump formation or a spongy-like substance. And that spongy-like substance itself is a rubber, right? So this rubber is the natural rubber, of course. The natural rubber, this natural rubber is obtained from latex, right? Now, this latex, what we are observing, actually it is a colloidal dispersion. Okay, it is a colloidal dispersion of rubber in water. Remember this. Latex is a colloidal dispersion of rubber in water, right? Now, when we observe about the structures, first thing that you need to know is that these natural rubbers, okay, this natural rubber, it has the monomeric species. The monomeric species which are involved in this particular case is going to be 2-methyl 1,3 butadiene. Okay, so a monomeric unit is 2-methyl 1,3 butadiene. Now this is also called as isoprene. Remember this. Okay, so it is also called as the isoprene. Okay, now when we observe its polymerization, so here n number of 2-methyl, so this is our 2-methyl, right? 1,3 butadiene. Once this thing is polymerized, okay, once this particular thing is polymerized, this becomes as CH2 single bond C CH3. Now this particular double bond shifts to the next position, so therefore we'll get it over here, CH single bond CH2, and this thing actually continues. Okay, now this is also called as the polyisoprene. Okay, usually we also call it by the other name, and the other name that we use for this is cis 1,4 polyisoprene. Okay, so this was about the synthesis of our natural rubber. Okay, now when you observe about this particular natural rubber, there are certain much more properties that we shall discuss in the next slide. So let's observe every single thing that what we have discussed point-wise. So the natural rubbers, these particular natural rubbers, actually they possess very good elastic properties. They undergo extensive, what we call it as an extensive extension under the slightest pressure. And hence it is also called as with the other name, and that other name is the elastomers. It is manufactured from the latex, which is a colloidal dispersion of rubber in water. Correct. Now this latex is obtained from the bark of rubber tree, as what we have already discussed, the way that they produce an insertion at an angle from the left to the right. Correct. So this particular rubber tree is found in India, Sri Lanka, Indonesia, Malaysia, and South America, right? So the structure, chemically, the natural rubber is a linear 1,4 addition polymer of isoprene. What is isoprene? Which we have already seen, right? It is also called as the cis 1,4 polyisoprene. Now, this particular polymerizations, which we have already observed, that is the isoprene unit gets polymerized in order to give us the polyisoprene, and that is nothing more than a natural rubber. Now, when we observe the chains, okay, when we observe the chain of these rubber, what happens is, let's consider that this is a chain of rubber over here. This is another chain of your polyisoprene. Okay, let's consider this is the polyisoprene polymer chain. Okay, let's consider this also as a polyisoprene, right? Now, here what actually happens is, between these, there is going to be the small or the weak van der Waals forces. Okay, so the van der Waals forces exist between the polymeric chain, due to which we can actually see that these rubbers are going to have a spherically curved structures, which we can actually elongate it. Okay, now these particular rubbers, because of the van der Waals forces, they are going to exhibit very good elastic properties. Okay, now due to this coiled structure, okay, due to this particular coiled structure, these particular natural polymers do not fit. They do not fit into the crystalline lattice. Okay, so they do not fit into the crystalline lattice, and hence we know that these rubbers are called as non-crystalline. Okay, so hence, as it is not fitting into this crystalline box or the particular crystalline lattice, we call it as a non-crystalline in its nature. Okay, now let's observe all these particular points one by one. So the cis polyisoprene consists of various chains held together by the weak van der Waals interaction, and that has a coiled structure. Okay, and hence it can be stretched like a spring, and it exhibits an elastic property. Due to the coiled structure, the natural rubber does not fit into the crystal lattice, and hence it is considered to be as a non-crystalline in the nature. Right? So this is actually how the structure, the molecular structure of the natural rubber looks like. Let's go further. So in the next case, we will observe about the synthesis of the vulcanized rubber. Now, when we observe about the rubber, simple rubber, we have seen that that particular rubber is actually very sticky. Okay, it is very soft and very sticky at the normal temperature, at the higher temperature. And as we cool it, it becomes brittle. Okay, now this natural rubber, I'm speaking about the natural rubber. So this natural rubber is actually very soft and it is very sticky, right? Now, what will happen? Because of this, this is exhibiting this particular characters at the higher temperature. Okay, now as we come at the lower temperatures, we will see that these particular rubbers become brittle and hard. Okay, now these natural rubbers also exhibit different properties, like they have very low water absorption capacity. Okay, so the water absorption capacity is low. Secondly, we also observe that they have very less tensile strength. Okay, so we can say as very low tensile strength. Okay, we can also see that the different things, such as it has the low abrasion strength or resistance. Right? Now, due to these particular properties, what usually happens is these rubbers get affected by the non-polar solvents. Okay, that means it is going to get affected very easily by organic solvents. Okay, hence these particular physical properties, as what we have seen, these can be enhanced. It can be improved by just addition of small amount of sulfur along with the other additives. So when you have a natural rubber, okay, so when we take a natural rubber, and this particular natural rubber is treated with calculated amount of sulfur under the presence of the different additive, specific additives. Okay, now during this particular condition, what will happen is this rubber gets stiff, it gets hardened. Okay, and this particular process wherein we treat the natural rubber with the sulfur at around 373 kelvins to 415 kelvins. Okay, now this particular process, we call it as vulcanization of rubber. Okay, so this particular process is termed as the vulcanization of rubber. So naturally, the vulcanization of rubber is nothing more than treating of a natural rubber with sulfur along with certain additives at the temperature of 373 kelvins to around 415 kelvins, right? So in order to get a stiff rubber. Now this rubber, what we get, we call it as a vulcanized rubber. Okay, so let's observe the points. So we have already discussed about this, that the natural rubber is usually soft, sticky, and it becomes even more at the higher temperature. While at the lower temperature, it becomes very brittle. Correct. At the lower temperature, it is going to become very brittle. So therefore, it has a large water absorption capacity, it has a lower tensile strength, it has a lower resistance to the abrasions. It is soluble in the non-polar solvent, okay, that is the organic solvent, and get easily attacked by the oxidizing agents, right? And this particular process, this particular thing, these all physical properties can be enhanced by using small amount of sulfur, by treating that particular thing with sulfur at a temperature of around 373 Kelvin to 415 kelvins. Okay, so that particular process, we call it as a vulcanization of rubber. So on vulcanization, what is going to happen is sulfur forms cross links at the reactive sites of a double bond. Okay, and hence this particular rubber gets stiffened. Now let's observe that particular structure, how it looks. Now, if you see over here, this is the point. Actually, here was a point where you get a double bonding, correct? As we had CH2 double bond C, CH3, single bond CH double bond CH2. So this was a monomer, that is 2-methyl 1,3-butadiene. But once it undergoes polymerization, we know that it becomes something like, so it was becoming CH2, single bond C, CH3 here, double bond here, CH, single bond CH2, and this goes, correct. The lower one also will be the same way, over here CH3, so double bond CH, single bond CH2, and it continues on the either sides. Now at this particular position, if you see this particular position and this particular position, sulfur is coming and interacting, and it is diminishing these particular bonds, and here is where it is going to form the covalent bonds with the two chains. Okay, and this particular process, we call it as a cross-linking. So sulfur, whatever we are adding, it is forming the cross-links. More the number of the cross-links, more stiff this particular rubber becomes. Okay, so this is how we can observe it on the other hand. Okay, so what are going to be the uses? Now, depending upon the how much amount of the sulfur is present in that particular vulcanized rubber, we can say that depending upon the percentage of sulfur, first thing, if we are using the 5% of sulfur in the vulcanization, then that particular vulcanized rubber is used in tires, okay, automobile tires. On the other hand, if the percentage increases from 20% to 25%, in such cases, it is used in preparation, it is used in the preparation of ammonites. Okay, in case if we are extending it to 30%, then this particular rubber is actually used in preparation of the battery cases. Okay, so depending upon the percentage, we can see its uses, right? So let's see, in the manufacture of the tire rubber of 5% of sulfur is used as a cross-linking reagents. 20 to 25% of sulfur is used for making ebonite, 30% is used for making the battery rubber cases. Correct. Of course, the last point is it was been discovered by the Charles Goodyear in the year 1839. Okay, so this was about the vulcanization of rubber. While the synthetic rubber is concerned, now this synthetic rubber actually it is a polymer, okay, which has the monomeric units. The monomeric unit as 2-chloro 1,3 butadiene, a very good substituent for the natural rubbers. Okay, now when we take these particular things and as we polymerize it, okay, so when we polymerize, we get, okay, first let's observe the structures. So monomeric structure looks something like CH2 double bond C, Cl single bond, CH double bond CH2. Okay, so this is our 2-chloro polymer. Sorry, 2-chloro 1,3 butadiene. Correct. Now, when we polymerize this, I'm extremely sorry. So when we polymerize this, what we get? We get over here CH2 single bond C, Cl double bond CH single bond CH2, and this particular thing continues. Correct. Now this is called as the poly. Okay, polychloroprin, and this was a chloroprin. Right. So this is the synthetic rubber. So synthetic rubber is like any vulcanizable rubber, like polymer, which is capable of getting stretched twice its length. However, it is going to return to its original shape and size when the stretching is withdrawn. Okay, so the majority of these particular rubbers, the synthetic ones, have been butadiene derivatives, which contains a carbon-carbon double bonds, as we have seen in the case of the chloroprin, right? So a synthetic rubber is either a homopolymer of 1,3 butadiene or its derivative, or the copolymers of 1,3 butadienes and or its derivatives with the other unsaturated monomers. So the first one, that is a neoprene, what we have seen, that is the polymer of the chloroprin, right? So this is again 1,4 linear additions of the chloroprin unit. Okay, now when we observe this, we need to understand where it is going, what its properties are, and where it is going to be used. Now these particular things are very stable. It is very, very stable to the aerial oxidation. Okay, it is very stable for the aerial oxidation. It is very resistant. Okay, it is very resistant to vegetable oils as well as to mineral oils. Okay, now when we observe its uses, it is used in the preparation of gaskets. It is used in the preparation of conveyor belts. It is used in the preparation of the printing rolls. Okay, so all these are the uses. So therefore, let's observe one by one. So it is very stable to aerial oxidation, superior resistance to vegetable and mineral oil, and it is therefore used in the preparation of hoses, gaskets, shoe heels, stoppers. It is used as an insulator and making the conveyor belts and the printing rollers. Okay, now Buna N is the next type of the synthetic rubber. Okay, it is also called as the nitrile rubber because this particular thing is a combination of the two monomeric units, and the two monomeric units that we have is the butadiene, again, that is 1,3 butadiene. Okay, this is one. Its combination with acrylonitrile. So I hope you remember the acrylonitrile is CH2 double bond CH single bond CN. Okay, acrylonitrile. So when we have this combination, okay, so what is going to be that as CH2 double bond CH single bond, sorry, CH double bond CH2, correct. So when this particular reaction occurs, it will give rise to, it is going to give rise to CH2 double bond, sorry, CH2 single bond, CH double bond, CH single bond, CH2. Now this is going to react at this point. So therefore, here we shall have CH2, now CH, here is our CN, and this particular thing continues. Correct. So this is called as the Buna N. Okay, so now that particular Buna N, what you have observed, okay, again the same way. So it is very resistant to the action of petrol, lubricant oils, and the organic solvents. It is used in making the oil seals, hoses, tank linings, and all. Right? So let us complete this particular session here. Thank you for watching. Do take care.